All right, so let's jump right in. So we are going to talk about a queue data structure, specifically the CoDel queue. It's a data structure that I came across while working on the Convex backend. And yes, I'm referring to the Convex database provider. The backend is an open source code base that you can look at yourself and just kind of get an idea of how they do certain things. So I came across this data structure, a queue. Specifically it's called the CoDel queue. CoDel stands for control delay. And I found it interesting, and so I want to share that with you. So I took some notes. I'm going to go through them as I talk about, the data structure, and hopefully this is something interesting to you. All right, so a CoDel queue. Like I said, it's a queue, and I think we all if you're watching this or you just, in software engineering, the concept of a queue, whether it's in real life, when you want to buy your Taylor Swift concert, but that would be a virtual queue, or you're in line at Costco or at your favorite grocery store. The concept of a queue is not, hopefully it's not foreign to you. It's everywhere. And typically when we talk about a queue, we definitely jump to the idea of first in, first out, right? FIFO. Well, what's interesting about the CoDel queue is that it has an adaptive behavior, and we'll see in the coming slides how in some cases you may actually be better off not following that standard pattern of just first in, first out. So the folks at Convex, they basically use their implementation of a CoDel queue is inspired by an algorithm that originally was meant for network programming, or specifically network routers, how to route packets over the wire, and there's a lot of queuing involved, and so that's the context in which that algorithm originally came about. So we're gonna talk about that aspect of things. We are going to go over the state machine that powers this CoDel queue. There really are just two states to really think about. So it's a sample state machine, which makes it elegant, and we'll briefly touch on the fact that the idea of being unfair can actually be a good thing. All right, so let's see, next slide. Okay, so typically with a traditional queue, when you're under load, you can end up with what can be referred to as a latency explosion, and I think you don't really have to think too hard to imagine why that would be something to worry about. If your queue is not being drained, or the items in the queue are not being processed at a good enough pace, then you can end up with a queue that's actually causing more problems than solving, as far as the availability of your system. And so with a typical queue, when you want to process an item, you usually just pop from the front, and that gives you the typical FIFO processing. The issue is, again, on the load, you can end up with all requests that are piling up. Your new request can then, because the old requests are now just sitting in a queue, you can end up in a situation where your new requests are also experiencing long wait times because they are being stalled because of the old requests. Also, it's possible that by the time you get around to processing a given request that has been in the queue for a while, its response or the output expected from it is actually no longer that useful. And so you can end up with a buffer bloat where your queue can actually be the bottleneck, essentially. And so from a good queue, what you really want is you want to be able to absorb the bursts of requests that are coming into your system. You want a queue that empties quickly, and you want to stay transient. Now, what you don't want, right, the state of a bad queue, you don't want a queue that is just kind of always full and just really adds latency to your overall, end-to-end request response flow. So, talking about the I guess the star of the show here, the CoDel algorithm. It was originally developed by Van Jacobson and Caitlin Nichols all the way back in 2013, and again within the network domain. And really the way it works is that they keep track of something called the sojourn time. You can just think of it as the time in queue, essentially. And your queue ends up in having two different states, right? And this is the state machine behind the data structure. And, like I said, it's only two states. And, that's part of what makes it very elegant. It's simple and really useful. So you have two states, the not dropping state and the dropping state, right? And it's about knowing when to transition between both. So typically the initial state is the not dropping state, right? And so the algorithm, when it's time to dequeue, right, it will check whether the sojourn time, right, the time spent by the item in a queue is actually greater than 5 milliseconds. If that is the case, and that it also has detected that sojourn time has been more than 5 milliseconds for a sustained amount of time, in this case 100 milliseconds, then the queue will transition from not dropping to dropping. And dropping here refers to dropping packets, essentially. And in the dropping state, what ends up happening is that when there is a dequeue operation instigated by a client or a caller, the algorithm, the queue in the background, before it replies, it will check whether it will do the dequeue operation, it will get the item, but if it's in the dropping state, it will check whether it should drop that particular packet, right? If it's in a dropping state, and I took note of this. So there is a variable called count, which in the dropping state, the queue keeps track of it, and that count, as you can imagine, it's an increment of, each time there is a packet drop, it increments the count, right? It keeps track of the count, but it also keeps track of when is the next time that it can actually drop another packet. Remember, all of this is happening during the dropping state, right? Which is the state in which you've reached a situation where your queue is at risk of being basically the issue of having a buffer bloat or just the latency explosion problem. You want to mitigate that, right? And so you are in that, let's call it a critical state, where you want to find a way to essentially stabilize or make your queue transient. So in that state, so you keep track of your count, how many packets have you dropped so far, and you also keep track of when is the next time that you are allowed to drop the next packet. And the way they do that is based on something called a control law, right? And I mean, the formula is not terribly important for the sake of, for the scope of this particular presentation, or, just talking about this. But really, the idea is that it doesn't just drop packets on every DQ while in the dropping state. It's actually done in a controlled way, hence the control law. Oh, sorry. Okay, we're back. So only drop if now is if now is after the time that was gosh, how do I say this cleanly, concisely? So you keep track of the next time that you can drop a packet, and if now is after that time, then you are allowed to do exactly that, drop the packet. Also, one thing to keep in mind is that you can the algorithm only drops one packet per DQ, so it's not a matter of it can drop some n amount of packets whenever there's a DQ, right? It's only one, and it's gonna move on to the next one, assuming that the queue is not empty. One thing to also keep in mind, and this is gonna be important once we move on to the Convex implementation of this algorithm. For this particular one, the original algorithm, they always maintain the FIFO order, first in, first out. What else? I'm trying to see if there's something that I'm missing from this slide that I haven't discussed. So we've discussed the fact that you have two states, so no dropping to dropping. So the transition, again, I guess one detail also to mention here is that the transition from dropping to not dropping happens, let's say, directly, right? There's no keeping track of a sustained interval like we did for the transition from not dropping to dropping, right? To transition from not dropping to dropping, it needs to be that the sojourn time is more than 5 milliseconds for a sustained amount of time, for 100 milliseconds. But going back from dropping to not dropping, it's immediate, right? Once it detects that sojourn time has come back, lowered back down to under 5 milliseconds, it just immediately switches to the not dropping state, which makes sense, right? You don't want to drop packets unless you find yourself in a situation where you feel like you have to. So the switch is immediate when, again, going from dropping to not dropping, which is meant to be the ideal state. It's also the initial state normally. All right. So moving on to the convex specific adaptation of this algorithm. They also have two states. In the case of convex, they label them as idle and congested. And for convex specifically, one thing that they do that's interesting is that they don't just transition the state, but they also, part of the transition also involves switching from the typical FIFO order to LIFO. LIFO meaning last in, first out, right? That adds a little spice. It spices things up, if you will. And also the way in which they do the transition is also different, but similar. So they go from idle to congested, and the way they decide that is they basically their criteria or criterion in this case. Well, actually, it will be criteria. Well, actually, I don't know why I'm arguing about semantics of which specific, whether it's criteria or criterion. I'm sure it matters, but let's just move on. The way they do the transition is they go from idle to congested by checking whether the queue has been empty for more than 5 seconds. Right? If it has been empty for more than 5 seconds, then they consider that to be a congested state. In this case too, the transition from congested to idle is automatic. Like as soon as the queue becomes empty, they just go to idle. They don't wait for some interval of time to decide. So with excuse me, okay. My mouse does this thing where it triggers the navigation. Anyway, so with the Convex implementation, again, they keep track of the last time the queue was empty. They always drain the items that are expired first. We'll see that in some slides coming up because I have some of the code in the slides to show. I think I mentioned the fact that going from idle to congested, they switch to LIFO. Oh, and expiration time, right? Expiration time really means sojourn time. Really, if you are mapping the implementation to the original CoDel, expiration time here, they get very lax when the queue is in the idle state. You have 20 minutes until you're considered expired, and you have 5 seconds when the queue is congested. It takes only 5 seconds for you to be considered expired, which makes sense because again, what we're trying to get is, we don't want the bad queue behavior, right? We don't want a steady queue. We don't want an always full or a queue that's going to add latency to our system. In the case of a database provider, they're doing request buffering, and you don't want the latency of your clients to experience high latency as they're making requests to the database, right? That's not how you you make your money, basically. You want to be able to absorb the bursts, empty quickly, and stay transient. So this is what this is all about, and that will explain why you have such a disparity between being in the idle state and how much time you get before you are labeled as expired, versus the 5 seconds where things are congested, and so they need to be moving things quickly. So looking at the code, so they have constants for what is considered the expiration time, right, for when the queue is idle, and the period or time interval that you get before you are considered expired when the queue is congested. You can look. I have a link at the end of the slides for where to go look at the code. It's really not hard to find. Just go to Convex backend on GitHub and look for CoDel queue. So this is where this code is from. It's pretty straightforward, right? You have the sorry. Okay, so you have the runtime. We don't really care about that. That's really the async runtime thingy. You have the buffer, which is the actual container for the items in the queue. They use a vec deck. And you will see that it takes in a tuple for each item. It takes a tuple. So there's the type of the actual tasks or items or requests, whatever is being enqueued, and then there's the duration, basically the deadline for that item, until once that deadline is passed, that item is considered expired. Obviously, we have the capacity. We have again, we keep track of the last time the queue was empty. we keep track of the idle expiration time, which is derived from the constants above and the congested expiration time. Again, coming back to the 20 minutes versus 5 seconds, you get 20 minutes when you're in the idle state and your system is calm. You can be patient. You can afford to be more relaxed in how you not relax, but you have some buffer essentially. And for congested, you're feeling overwhelmed or overloaded, and so you are more ruthless, or requests are likely abandoned. Let me see, what else do I have as notes? So in the case of Convex, we just basically track when was the last time, when was the queue empty last, right? And we do that. This is the predicate over here. It's pretty straightforward, right? So we use the last time it was empty, and we add that to the idle expiration time and compare it to the current instant. I think that's pretty easy to grok, I think. Pretty easy to understand. Okay, so this is so the push here, that's obviously when you are pushing items into the queue and queuing. So each item gets a different sojourn time, or in the case of Convex specifically, a deadline, and that is based on the current state, right? Which makes sense because again, we have that separate time to expiration, right? 20 minutes, 5 seconds. And to know which one to pick, we need to know whether we are in the idle state or if we are in the congested state. And based on that, that gives us an idea. Well, it lets us know how to set the deadline for the item that we are in queuing. So I wrote here that each item gets stamped with a deadline based on the queue's current mood, patient when calm, and patient when stressed. Now, when it's time to dequeue, right, this is where the interesting thing happens, right? So rule number 1 is you always want to drain the stuff that is expired. Now, in the implementation here, the queue doesn't, unlike the original algorithm, right, the CoDel or the original CoDel algorithm, in the Convex implementation, the queue itself, the data structure, doesn't drop the items. But if the item is expired, it will respond with that item first, right, during the dequeue operation. It will respond with that and it will provide you with the information that this item that I just dequeued is actually expired. So now it's up to the caller or the client to decide what to do with that information, right? Depending on how the system is architected or configured, especially if you end up in a situation where you have a metastable, I think that's what it's called, metastable failure. Those are nasty, right? You don't necessarily want the data structure itself to be making those decisions, but instead the clients, the things in which it's embedded, the systems that are using it as a backing data structure, you want those systems to be making the decision of, okay, this item is expired, it has reached its deadline, so let's drop it, right? So the queue itself doesn't make that decision, but it gives the metadata to do so, which is the expired in queue. So if you look at the signature of the pop operation, so you have the optional tuple of the item, or the item, it's a tuple, so there's the item, and you also get whether or not the item is expired. So we can walk through each section of the code here. first we figure out what is the current instant. Then we extract the item from the buffer. Sorry, we extract the item from the buffer. We compare its expiration time, and usually the item that we get from the queue, from the buffer, the way it's set up, you always get the oldest item first, right? And so we check whether that item is expired, right? If it's expired, then that's the one that we serve. And we let the caller or the client decide what they want to do next with that information, right? Otherwise, if it's not expired, then it's really based on whether or not we are in the idle state or we are in the congested state. If we're in the idle state, then we do the typical FIFO extraction. Otherwise, we do the LIFO, right? Again, LIFO is last in, first out, right? So really, we are taking from the back of the queue. Here we match, right? We check if we have an item, right? If the queue is not empty, or if the queue is empty, then we have nothing really to return. We just return a none, right? But if there is an item, the queue is not empty, we either return an item that is expired, or we return an item that's either at the front or at the back, right? If an item is expired, which is an item up front, then we return that, and we provide the metadata to also inform the caller of that fact. Otherwise, we return whatever we got, whether it's from the front or the back. Again, it will be in the back, right? It will be from the back if we're in a congested state. Otherwise, it's from the front. Again, we're dealing with state machines, right? One thing that you want to think about is your invariants. One invariant that I wanted to note as I was taking notes, notes on this data structure. So I wrote, in LIFO mode, you'll never get an expired item because expired items are always drained first, right? This ensures that the caller handles expiration properly. And that's what the first if branch gives you, right? In the first if branch, we check for the, okay, we're back. For the first item, we check what is the oldest item, and if the oldest item is expired, then we need to return that. That's just the way it works, regardless of whether or not we are in the idle or in the congested state. So I just wanted to know that I guess you could say that that's an obvious one. I'm sure if you were to dig deeper and deeper and deeper, there are a bunch of invariants that you can come up with, but just as a way to introduce ourselves to even just this data structure, I think that's one that we can quickly come up with and make note of. All right, I think we've covered everything. I think we covered, in terms of the actual some implementation details that matter, right? For the CoDel queue, the Convex implementation, that is. So we've covered the actual structure of the queue, the predicate of determining whether it's in the idle or in the congested state. We've covered what happens when you try to enqueue an item and the fact that you need to decide how to assign the deadline based on whether you are in the idle or the congested state. We've covered the dequeue operation, right? And the fact, again, going back to the invariant, we always check for the oldest first because we want to drain the expired stuff as we are dequeuing, and we provide the metadata to let the client know that this is expired, so the client can do what they want with that information. We've covered the fact that if we're in a congested state, we take from the back instead of from the front. All right, so in terms of performance benefits, as you can imagine, this enables us to have a sustain a lower tail latency, right? Without lots of complex configuration, because queuing can get really complex. There was a whole queuing theory field that you can study. I mean, queues are really everywhere. Like, it's just, and I mean, it's easy to see why, because you have time and the need to make something happen. And the reality is there are a lot of processes or things that come about that it just takes time to realize them, to produce them. And whether it's implicit or explicit, you want some level of fairness. And so it's very easy to see how queues come up in so many domains, in so many practical things that happen in the real world, or even in the virtual software, whatever, technical world. So again, performance benefits under load. You're able to serve fresh requests quickly. Again, that's because of the LIFO behavior, right? We are not letting we don't want the queue. We want the queue to stay transient, and one way to do that is to not let older items necessarily block newer items from being processed. Because again, remember, it could very well be the case that a significant number of the items that are basically stagnating at the front of the queue are no longer relevant or useful, right? So the LIFO behavior definitely helps with avoiding the latency explosion problem. All requests get expired gracefully. Again, on the load, when you're congested, you only get a 5-second timeout. And then it makes it possible to really figure out, whatever strategy works for you in terms of shedding your load as requests are coming in. Again, this is for a database provider. The whole idea is you want to do adaptive request buffering until things come back to normal. So key lessons again, adaptive behavior instead of static. This can really help. Now, there are domains in which having static predictable behavior known even, just a compile time is preferred. I think I'm alluding to real-time embedded systems, or, that kind of software where you actually develop with the idea of worst case scenario in mind, and you want to limit how dynamic and adaptive your system can actually be, because you are very stringent on knowing exactly what's going to happen no matter what. We're not talking about that. That's a separate domain or whatever discussion. But typically in a distributed system, like, again, Convex, a database provider, it's reasonable to want to have a queue that adapts based on the system load, right? And again, it's based on that adaptive behavior, it will be okay for some period of time to be unfair, and that can actually be fair to everyone, all the clients, right? Instead of having one or a very small percentage of the client request essentially ruin the latency for basically all the other clients. Yes, so another thing to note here is that, again, Convex brilliantly adapted a networking concept for the particular domain, which is serving database requests. So when to use a CoDel queue, request buffering, when you care about buffering requests that are coming in to your system, you want to be able to have good queue behavior, right? Good request serving on the variable load. You care about the latency of the requests that you serve. Again, there's not the elegance of this is that you don't have so many things that you have to tune in terms of parameters and all that. You really need to care about sojourn time, right, which is really the time that it takes for a particular work item. The time that a particular work item takes in a queue, that's not so hard to account for in your design. You want to watch out for how you assign the different timeouts for when your system is, I guess, in its ideal normal state versus its congested state. And queue capacity is an obvious one. All right, so I think that was it. So again, we have the original paper. Excuse me, the original CoDel paper. I have a link to it. I'll have it in the video's description as well. Same thing for the Convex backend. Again, it's an open source source code, right? Open source code base. So I have no affiliation with Convex. I just happen to think that the people working there, for the most part, I think it's fair to say that they know what they're doing. And so I was just checking out the code base and I came across this. They have a bunch of other stuff that are interesting. This is just the first time that I'm sitting down and actually taking notes about something that I find in a open source code base and actually wanting to talk about it. So I may actually end up doing this more because they have, off the top of my head, I can think of another one or two other things that I may make videos about as well. So yeah, we'll see. So I hope this was useful. There was some information here that was interesting, and hopefully this gives you the intent of going and looking at the code base, the Convex backend code base, or just in general, just think about the libraries or frameworks that you use for the third-party libraries, obviously, and frameworks that you use, and check out the code base and just see what's in there. You may be surprised to find some things that are interesting just for you to learn from. Something that can even help you in working on your own internal stuff. All right. Thank you.